called entropy. Entropy has units of joules or energy per Kelvin per temperature. So as I just said, temperature can in fact play a role, and that is seen here in these units. Now, many of you may have heard of entropy before, and it was probably introduced to you as a measure of disorder in the universe. But it turns out a better description is actually that's a measure of how distributed energy is throughout the universe. And the second law of thermodynamics simply states that as the universe expands, remember the universe is constantly expanding, the distribution of energy through the universe also expands. And so it's this insight that leads to the second law of thermodynamics, that is simply that the entropy of the universe, distribution of energy through the universe, is constantly expanding. And so because it's constantly expanding, we then take from that a process is spontaneous if and when it increases the overall entropy of the universe. So one way to get a handle on entropy is actually to look at the statistical approach. So we're going to zoom down and pretend that we have 3 particles, and to these particles I can distribute 3 units of energy. That's this little squiggly e. It's just units of energy. It doesn't matter what those units are. And so if I only give whole number units of energy, that means I can have 0, 1, 2, or 3 on any given particle. But again, it has to sum up across those 3 particles to a total energy of 3. That's all I have to distribute. So we can graph this as each particle number, how much energy each of those particles has, and then we consider different ways of arranging the energy, of distributing it out. So let's start by putting 3 units of energy on one particle, and then 3 minus 3 is 0, so I have 9 units of energy left to give the other 2 particles. Well, I can do this by giving all the energy to particle 1, none to 2 or 3, or I can give all the energy to particle 2, or I can give it all to particle 3. And that's it. So having this distribution of energy, 3 units on one particle, in this case, has 3 ways of being accomplished. Let's try another way of distributing the energy. We can give 2 units of energy to 1. That leaves us 1 unit of energy. That could go to a second, and then the third one has to have 0. So I can start by just giving 2 to 1, 1 to 2, and 0 to 3. Or I can swap these 2 and give 2 to 1, 0 to 2, and 1 to 3. Just skipped ahead. I can also flip this around and have 1 with 2, 0, so on and so forth. And it turns out that these 6 show all the different ways that I can arrange it. So having this distribution of energy in form has 6 ways of being done. And then finally, the last way I can do this is just to give every particle 1 unit of energy. And unfortunately, there's only one way we can do this. If I try moving this over and swapping this amount of energy with this amount of energy, it just looks the same. So there's just only one way. All right, so then which arrangement is most likely to happen, just statistically? If I have 3 ways to arrange with one particle 3, 6 ways to arrange with one particle 2, 1 with 1 and 1 with 0, and only 1 way for them all to be arranged, that means I have 10 different ways of arranging. So all else being equal, the probability of being in one of these is 3 out of 10, and here 6 out of 10, and here 1 out of 10, which means statistically, I expect that this case is going to be what I end up seeing if I just let energy distribute itself across my system. So some language to introduce here is that those distributions of energy, being 3 to 1 particle, 2 to 1 particle, 1 to 1 particle, or 1 to all my particles, those are called configurations. It's a type of energy distribution. And then a microstate are the specific ways that I can achieve that configuration. So those are each of those little graphs. And then which configuration will I see? Well, we just said it falls down to statistics, and statistically, the one that's most likely, the configuration with the most microstates, is referred to as the dominant configuration. And so we can actually think about measuring whether or not a process is spontaneous by counting the number of entropy states, the number of microstates to a configuration from that change. And here's another word for you. It's called weight. weight is simply the number of microstates that a given configuration has. We just give formal labels to everything. And we can relate the weight of a configuration to the entropy associated with that configuration using something called the Boltzmann formula. And that comes out to entropy is Kb times the natural log of W. And Kb, by the way, is just solved for the gas constant divided by Avogadro's number of particles, and it's this number, empirically derived. And we can see just from this formula then that the configuration with the most number of microstates will then be the largest entropy. So that sums up here. So one thing I want to emphasize is that just because we know that weights and entropies come from statistics doesn't mean that we always have to write down every single microstate. That gets very tedious very quickly. Instead, we can use this mathematical formula to help us out. So let's have an example. If we consider 300 students, of which 3 have an energy state of 1, and the other 297 are asleep and have no energy, then in this case, our number of particles is number of students. Our energy state with 1 is 3 students. Our energy state with, or our number of particles energy state at 0 is 297. And so our weight is just plugged in for 300 factorial divided by 3 factorial times 297 factorial. And we can actually get a number out of this. All right, so let's go back to this expansion of a gas. If we consider a gas that's expanded from a container to a container twice its size, we can actually say something about its entropy without counting up microstates. Well, how can we do that? First, let's focus on an individual particle. And let's consider that for that particle, when it's in a box of volume V1, it has some number of states available to it. And when we double the size of that volume, it will have twice the number of positional states available to it. So without solving for W, we can just say that the final weighting is just twice that. It has twice the amount of space. And so delta S, again in thermodynamics, delta means final minus initial. We get delta S is Kb times natural log of 2W minus Kb natural log of W. If you're familiar with the math of natural logs, we can rearrange this to just natural log of 2W over W. These cancel out, and we get that the change in entropy is Kb times the natural log of 2. But again, this is for one particle. So what happens when we go to multiple particles? I actually have an in-class activity planned for you guys. So you'll see on each of your tables there's a pile of coins. And each coin, if you flip it, can either land heads up or tails up. So that means I have 2 possibilities for every given particle. It can either be heads or tails. So without even playing with your coins yet, you can consider if there were 2 coins, right? I can either have both heads up, both tails up, or one can be heads up and one can be tails up. And in this case, that configuration has 2 microstates. So I'd like you to go ahead and do now in your groups is figure out how many microstates there are when I have 3 coins. I'm seeing lots of microstates on your guys' table. Here's what I think you guys should have. What's really cool about this now is we can take a look at counting up the number of states available, and we find that in the case of 1 coin, there's 2 outcomes. In the case of 2 coins, there's 2 coins that each have 2 outcomes. And in the case of 3 coins, I have 3 coins that each have 2 outcomes. And so mathematically, you can generalize this exponentially to say the number of outcomes raised to the power of number of particles. So if we go back now to our gas in the expanding container, we can say that for Avogadro's number of particles, I will have, again, 2 for each of those particles. So we're going to get 2 raised to the power of Avogadro's number. So that means that our change in entropy now is Kb times natural log of 2 to the power of Na. And if you're familiar with exponents and natural logs, it turns out that we can take this exponent down, and we get Na times Kb natural log of 2. We get that the change in entropy is just R times the natural log of 2 for 1 mole of gas.